Sarah's factory produces millions of heavy-duty grocery bags daily, but the line is bleeding cash. Every few minutes, a normal bag shreds under stress testing. Factory management is completely baffled. According to their daily reports, the average tensile strength of the paper easily meets the passing metrics. As far as the baseline numbers show, production is completely safe. They are falling for a statistical illusion based on what engineers call point estimation. This is when you use a single numerical value, like a sample mean or a sample variance, to approximate the overall reality of your entire population of products. The mathematical trap is that a point estimate only identifies the data's center. If you zoom out, you find a massive, scattered cloud of extreme high and low data points. The average is totally blind to this unpredictable edge variation. To stop the line from producing defective bags, Sarah must move beyond the false comfort of that central average. She needs to mathematically map those unknown extremes where the tears are actually happening. Fixing a broken system begins with strictly defining the boundaries of its chaos. Sarah steps off the physical factory floor and pulls the historical material data. She begins charting out the precise statistical boundaries of these tensile strength failures. Her first escalation is building a confidence interval. Instead of a single dot, this calculation gives her a distinct range, allowing her to locate exactly where the true mean actually exists within the noise of all that sample data. But the mean isn't enough. Look at this calculation for a prediction interval used to find the exact load failure of a single future product. Notice it requires a much wider range than a confidence interval, resulting in this wide numerical spread from 6.16 to 21.26. Next is a tolerance interval, which sets the exact boundary guaranteeing 90% of the products will survive. The calculation resolves at the bottom, proving the vast majority will safely hold loads between 5.67 and 21.74 megapascals. By stepping from a simple point estimate through these three expanding intervals, an engineer stops guessing about the present and starts actively predicting the future limits of a physical product. For Sarah's grocery bags, the specific physical variable under investigation is the hardwood concentration in the paper pulp used on the line. She applies hypothesis testing to the historical run logs. This lets her statistically prove that a change in hardwood levels directly causes a change in tensile strength, successfully separating a true signal from random manufacturing noise. Then she uses regression analysis. This statistical technique builds an empirical model mapping the precise relationship between the hardwood inputs on the x-axis and the product yield on the y-axis. By relying on the method of least squares, the regression model can intake highly specific pulp mixtures and instantly output accurate strength predictions for the resulting paper. To be absolutely sure, Sarah analyzes the residuals, the distances between the real data points and her projected trend line. This step verifies that the regression model is a mathematically adequate fit for the physical data. Defining an empirical regression line strips away the chaos. It proves the mathematical relationship between material inputs and product strength so strictly that random defects have absolutely no room left to hide. With the model verified, Sarah initiates a targeted design of experiments using 4 highly specific hardwood concentrations: 5, 10, 15, and 20%. She takes her optimized empirical model and programs the exact hardwood parameters directly into the physical factory floor machinery to re-engineer the bags from the ground up. The variance completely collapses. The extreme outliers vanish, the data tightens symmetrically around the target, and the catastrophic tearing on the line ceases completely. This is the practical application of Six Sigma, using historical performance to drive a predictive engine for the line. Sarah systematically progressed from a simple point estimate, built out strict confidence and tolerance intervals to define the boundaries of failure, and finally created a robust empirical model to dictate the outcome. Mastering this mathematical progression allows an engineer to actively control manufacturing reality, eliminating waste and guaranteeing perfection.